All right, here we are, part 2 of multi-threaded programming. Now, we've talked about race conditions and how they can be caused and how bad they can be. Let's talk about how to fix it. There are two primary ways to deal with these shared resources, either by locking the resource or by being notified when it's available. Now, the most obvious way to deal with these resource contentions is to lock the resource. That's where we give one thread the ability to say, hey, I'm using the resource right now. I know there are other threads that might want this, but I'm incrementing this global variable right now. And while I'm incrementing it, I need to be sure nobody else modifies it while I'm in the middle of modifying this, right? So we'll lock the resource, probably with something called a mutex, or we may implement our own version of mutex using a spin lock. What that'll do is say, I own it. Only I can use this resource. While it's locked, you modify the resource, and then when you're done with it, you unlock and allow the next thread access to it. Okay, but the downside of that access pattern is you tend to end up with a lot of, hey, can I have it? Hey, can I have it? Hey, can I have it? And you're sitting in a loop. The name spin lock even sort of implies that you're spinning, asking to lock the resource. Can I have it now? Can I have it now? Can I have it now? And you can waste a lot of time when there's nothing available or nothing to be done right now. An alternative is to set up something a little bit more complicated, an event, when I will notify you when it's available. That will allow, an event will allow a thread to go to sleep, meaning just turn off that thread and wake it up when it's ready. What the benefit of that is, if you have other code to run that would like to get onto this CPU, you can, the operating system can sleep one thread and wake up another thread on that same core, and then let the other thread run on that resource for a while until it needs to wake you back up, and then it can put the one thread to sleep, right? I've talked about running one thread per core, but we can actually run more threads than we have cores. That comes in pretty handy, particularly with PC architecture where we don't know how many cores the user might have. Maybe we designed for a 6-core system and the user maybe only has 4, right? So somebody's going to have to share in that case. And the operating system sets all that up for us. Okay, first let's look at the concept of the mutex. The mutex lets us lock a resource. When we say lock a resource, really we're locking the mutex itself. So I've got here a global variable of type mutex called glock. And here I will lock the mutex. I will lock the mutex before I access that shared variable of the GA, and then I will unlock the mutex when I'm done. Now, a couple things. Don't forget to unlock the mutex, and don't lock it when you don't need it. Like, a common mistake is to lock the mutex up here before we do the slow work. We don't need the mutex while we're doing all this slow work. We only need it to protect this one tiny thing. And that's important. The reason that's important is because the lock, what it actually is going to do is ask the system, can I have the lock? If another thread already has the lock, the system's going to say no, and you'll be stuck there. That will cause the thread to stall right here until it can get the lock, okay? And so that means if two threads hit that at the same time, one of them is going to get the lock, the other one's going to stall, and you want to minimize how long that other thread is stalled. So only put it around where you need it. Okay, now speaking of stalls, a true mutex, if you use a true mutex, and we will in the lab, use a true mutex, Windows is going to anticipate that this resource you're trying to lock could be shared not only by another thread within your same program, could be shared by another program running on this machine somewhere. And because of that, it has to go all the way out to Windows to lock everything. And that can be a fairly slow process, as I'm sure you can imagine. So what we can do is implement our own version of a mutex that we'll call the spin lock. And we call it that just because what it does is it tries to lock the access, and if it fails, it just tries again. It tries again and tries again until it can get it. It just spins. It sits and spins, trying again until it gets the lock and then proceeds. So we'll call that a spin lock. How will we implement it? It'll look something like this, little class where we have a volatile. Remember, it's volatile because it might be accessed by multiple threads. Just, is it locked? It's a Boolean saying, is it already locked? And this is actually going to be a shared resource now. Okay, that's all well and good, but how do we implement that spin lock? That's the trick. We will be making use of one of these atomic instructions. Atomic, of course, originally meant something that could not be subdivided any further. Since then, we have split the atom, but that's a different story. These atomic operations are operations that can do these sort of complicated things, but are guaranteed will not be interrupted by another thread. What we saw in the previous example was the simple instruction ++GA took 3 assembly instructions, and another thread could interrupt at any step, any one of those 3 steps. These atomic operations cannot be interrupted. So we'll have 2 we'll take a look at real quick. We'll look at this interlocked exchange and a slightly more complicated interlock compare and exchange. So interlocked exchange, what does that do? It takes an address and just says, hey, what's at that address? Whatever's at that address now, I want you to return that to me. Just return whatever is at that address now, and please change it to this value. So it just says take value, stick it in that target, but give me back whatever was in target before. Okay, that's that. Interlock compare exchange is very similar, but it has a compare injected in the middle. It says, hey, what is at destination right now? If destination happens to be this value, then I want you to change it out to give me, to put in that value. And while you're at it, no matter what, whether it was or it wasn't, return back to me whatever was in there. Okay, so that's a couple of these interlocked exchange functions that we can use to implement the spin lock. Now, I don't expect you would visualize right away how you could use that, but let me show you how we do, and then I think it'll be more clear. Okay, here is a simple spin lock. First of all, let's just cover this one. Sleep just means release the thread. I don't have anything to do. Let the operating system have some time on here. If there's another thread that wants to run, now is a good time for them to run. And the argument to sleep is how long you want to sleep until you are reawoken. This is typically in milliseconds though. So 1 millisecond is like a really long time in video game time. Some systems let you sleep 0, which would say if there's something else waiting, let them run. Otherwise, just kick me right away. Okay, so that's what sleep does. Here is our interlocked exchange, and let's see how we're using it. We are going to be, the address we're going to be giving it is the address of our Boolean variable. So we have this shared resources Boolean variable. Now remember what interlocked exchange does is it sets it from whatever it used to be true. So no matter whether it was locked before or not, it's locked now. And what I want you to do is return the old value. So if it was already locked, I'm going to get a true back. So if it was already locked, I sleep and come back up and try again. And if it was already locked, I sleep. If it was already locked, I sleep. So this is our spin. As soon as you try to lock it and it was not locked, a false will come out. And that will say, hey, we locked it. And now it will be true, because the other thing this instruction does is tell me what it used to be and set it to true. So if it was not already locked, we're going to set it to be locked, and the return value will be false, so we will skip over this while loop and return from the function. So a spin lock will use interlocked exchange to spin. How do we, so how do I unlock then? I unlock simply by setting it to false. This is just a single operation that will not get interrupted, so we can safely do that. Also, it mentions here, we should only unlock the thread if we are the one who locked it, so we can be pretty safe accessing it. Okay. Okay, now I mentioned before, you've got to remember to release your locks. Otherwise, the next thread that comes along is going to say, hey, can I have that lock? And the answer is going to be no. And unfortunately, it's going to stay no forever. And that's going to cause that other thread to get stuck. And it can't move on. So forgetting to unlock is kind of a problem, but it's an easy mistake to make. As your code gets complicated, sometimes there's like you throw a return in there somewhere in the middle of your function, and lo and behold, you forgot all about that unlock. That's farther down. You didn't get to it. Okay. So there's a way we can protect ourselves from that. The technique called scoped lock. The idea is that we create something that will lock the lock when it's created, and it will automatically unlock it when that thing is no longer used. How do we pull that off? Maybe there's a clue in the name. Now remember, in C++, we create a scope with curly braces, right? And if we create a variable inside here, like, I don't know, I think thingy, let's make it a variable of type thing t, semicolon. I just constructed a thing on the stack, right? I asked C++, give me a little stack memory and call the thing constructor on that address. That's what I just asked. And then when thing goes out of scope, right here, that'll be popped off the stack and the T will be destructed. Boom. We can use that technique to have the destructor automatically clean up for us. And here's how we might implement something like that. In our constructor, we'll take as an argument the spin lock that you want to lock, and we'll lock it. And then in the destructor, we will call unlock on that same thing, so that automatically, when this thing goes out of scope, we will unlock and not be able to forget to unlock that mutex or that spin lock. This is the same technique we used for the profiler, and it's a nice little trick I like to use sometimes. Putting that into practice looks like this, where we used to have a lock-unlock pair. Now we have a lock, and then we simply let that scoped lock fall out of scope and automatically free itself. This protects us. If the code was more confusing, that maybe like you could lose track of exactly what the flow through here was, and it could sort it out for you. Not a big deal. In fact, when we do this in the lab, I don't think I would not advise using a spin lock. I'm sorry. In fact, when we do it in the labs, I would not advise you to use a scope lock in all cases, because sometimes you do want to control exactly when you release the lock so that you can really minimize how long the lock is held. Okay, so that's locks, and scope locks, and mutexes. Let's talk about atomics. Wait, didn't we talk about atomics? Well, we talked about the interlocked exchange atomic instructions. There's a whole bunch of, now in standard C++, bunch of atomic templates. And what they are is basically you can declare a variable to be an atomic type, like an atomic int, for example. So here I've just declared std : atomic, and it's a template, so we have to say what data type it is. I'll make it an int, and I'll call it my int. Now, what does that do? What that means is if you do plus plus on it, or plus or minus minus, or many of them, plus equals, a bunch of these instructions on that type, it will implement them in an atomic way. So let's see what that would look like in action. Here's that same proc A where I have that same shared resource, and now I've declared the shared resource not as a volatile int, but as an atomic int. And because of that, I don't need to add any protection to it. I can be certain that that resource is already protected. How can that be? Well, if you look at the assembly and see what's in there, what you'll find is it probably compiled out to something that looks more or less like this, where it is making use of those same atomic operations that we were just talking about. So that's part two. We've talked about what race conditions are and how we can use mutexes, spin locks, and atomics to protect our shared resources. So let's take a break. Good time for a break. Come back here in part three, and we'll talk about how to design a system and leverage this multi-threaded concept.